just had to look at my notes a lot.
Yeah, it's clear today.
Wait, what'd you say, Bryce?
Come on, or high.
Sounds better than. Oops. All right. Shut the door.
I like it. Bryce, you like that shirt?
Go dogs.
Read
Just got it last night.
Read it for us, Bryce.
Man,
Bryce, what's that say?
Bryce,
you want to read the shirt? What does that say, Bryce?
Implied is state champions too. Anyway.
I just want to check the shirt.
Let's go back here. Let's let the people at home know. Who's it? I don't even know if anyone's right here. New threads. Let's go. There we go. All right. So we're back. There it is. There it is right there. Subcategories of Matter. Just got in last night. It was, oh man, so good. We had smaller than 2 last night, and I got to unveil it. I also got a glass, just a glass, and then a coffee mug. It says the record, and says national champions, and on the back side says the schedule. Very classic looking. I'll show you a picture later. I didn't take a picture of it, but I'll show you the one that I ended up going with. So here we go. What are the 4 subcategories of matter? My face pop up. Did my face stay in the corner at times? Okay, it's good there because this spacing has to detect. Oh, it looks like it's cutting off. It might not think my shirt is me.
Yeah, it's kind of just white.
Up in the upper right hand corner. You see that? Mm-hmm. Oh no, that's okay. I'm just really small. I can make it bigger. Leg up bigger. That's why it's like that.
Yeah, I guess. So if we go down, we go down.
Alright, back again. Here we go. Sorry. I'll go. I was pre-muted. We didn't have anything else to do other than the front side of the classification of matter page. All right, so what I want you to do is get that classification of matter page out and show me the front of it. Just like this. Make sure you go like this. Show it to me. I'm going to just kind of take a glance. This was due. This was a due today, so I got to emphasize 2 different types of due. And I don't mean doo-doo, but there's due and there's due. So what I want, whenever I have, usually a one-night due date is a DO, is a due. Do it. Do it, and I don't expect perfection. I expect a complete attempt. The only thing that would lose credit are blank answers. It's the only thing. Incorrect, filled-in answers can fool me. I'm letting you willingly fool me on a DO check. Hello? Because I'm just looking that you're attempting it. Now, if you just put in blank stuff, does it help anybody? Like, if you put in just like nonsense junk, does it help anybody? No. Like, at least try to think about it. Like, just spend a couple minutes and think about it. Because the net result is to benefit you. Anyway, then there's a DUE due, and this one is as I'm looking more at accuracy. And sometimes I'm looking at like the whole page. I'm looking at a lot of accuracy across the whole page. Sometimes I have like a couple like checkpoint problems that I just decide that day as I'm checking. All right, this one I'm checking for the answer of because it had a specific kind of nuance that if you know this one and you did it right, I know you know how to do all the rest of them. Are you with me? And so I'll like flip over a page. I'll look at like 2 from this side and 2 from that side just to kind of verify that you got the depth and the nuance. Hello? So that is that. Everyone who's here seems to have done it, unless I'm seeing it wrong. Oh man. Oh wait, you are your size wrong, student. Yep. Madison? Oh, she's not. Aaron, AJ. Don't worry, Bryce. You're Cam. Jaden. Emily. Caitlin Woodard. Come on, Caitlin. No, she just does. Okay. All right. Good. So I promise you, I'm gonna have some grades here soon. I've already graded your lab safety tests. They don't count as a test grade, but it'll still be a nice little quiz grade to have. I promise you I'll have grades soon. Just bear with me here on that note. You don't need it? You already had it? Huh? Oh, because I gave it to you Friday before. That's right. This only applies to a few students in 4th, actually. Okay. 4 subcategories of matter. What are they? Look at you getting it. We got element, compound, heterogeneous, mixture, homogeneous, mixture. How about abbreviations? Watch this. E, C, H, T, H, M. You okay with that? Those are 4 subcategories of matter. Good job, Jaden. 4 subcategories of matter indicates under the header of classification of matter, you've got pure substances and mixtures. Pure and mixtures. Yes? Okay. And the definitions, we got those. These can be physically separated. These can only be chemically or nuclearly separated. Hello? Okay. Let's see. Homogeneous. What's another name for homogeneous? Solution, and the abbreviation we use for that one is SOLN. Okay. Heterogeneous. What's the most difficult one to identify? Colloid. You've got colloid. You've got suspension. And then you just got the general kind. General heterogeneous mixture. Why general kind? Things like pizza, salad. Pizza and salad isn't really a suspension. It's a heterogeneous mixture. There's a broad category, and then there's some specific ones in between. Most salad dressings, besides ranch and Thousand Island and French, those are colloids. But most salad dressings that you have to shake up before you do it, like Italian or like Greek or whatever, those are suspensions. Are you there? So really, suspension is just to delineate between colloid and suspension, and not just generalized. Are you still following right now? Okay. 4 subcategories. Neat. Great. Thanks. Evan's got all this. Can you name all the phase changes matter can undergo? Evaporation, condensation, sublimation, deposition. Look at this guy. How about melting and freezing? Yeah. So in your foldable, your phase change is foldable. We're going to add these in here with some arrows and label your energy arrows. What do you think energy has to do with phase changes? So energy, which direction does it flow with respect to the substance?
Solid, more energy, goes to liquid, more energy goes to gas.
What do you mean? What's the direction is the more energy going? The more energy is going where? Where does it go to make the solid become liquid? Where does the energy that makes the solid turn into a liquid? Where does it go? How about inside the substance? In between the molecules, which is to say, more simply, inside the substance, right? If you take, this isn't your calculator, is it? Yours just sitting here? Same thing with that one, right? Give me 13, I need to label these, and then put them up. 13 and 7 for 40 period. Peak. Oh, whoa. Okay.
I just put evaporation.
Who else? Did who's number 8? Ray. Ryan, do you have your calculator?
I do.
Okay, good. 12. Zach is not here. Is that yours? What's your number? Is that your number? No, you're not that. You're number 5. Can I get your calculator? Yours right here. This is 14. Okay. Who has number 12? You have number 12? But you're number 11. That's fine. That's fair. That was okay. So we can make a little mistake. Did you think you were number 12? You were number 12 for a little bit, then you lost the student thing. Okay, good. Just want to get on that boat. Next. What does energy have to do with phase changes? I was going to take that calculator and say, okay, if we take a solid calculator, how would it go about melting? It would have to absorb heat, right? Heat, energy goes in. Do you know a word that means heat in? Do you know a prefix that means in? If you go outdo, but it's too cold, you need to go endo. That's it. Good job. You gotta go endo. Endo. There we go. Endothermic. It absorbs endothermic, and if it releases, then what's the opposite? Look at you guys. There you go. All right. So on your foldable, I want you to kind of do this in between the margins. Let me go to your foldable picture to show you. So like on your foldable, I want you to add a little bit here, sort of like this. I want you to add on your foldable where you have those energy lines. I want you to put along the arrow going to the right, which should go from solid to liquid to gas. That's, y'all can't see that, can you? That's a terrible color.
I can see it. I got 20, 30. I got 30, 20.
We don't have 30, 20.
Okay.
If
In.
it works.
Is that better? Out. Hello? Is that, you follow that one? Can you see that better now? Half better?
Huh?
Did you say half better?
No,
Oh. In is endothermic, out is exothermic. And that is what you need to add to your foldable in that space. Okay, neat. Great, thanks. Awesome.
Can you open it up?
Okay. Great. Great. What else have you to say?
Go dogs.
Right, yeah, definitely go on. Would you like to add anything else to this part? Have I lost you yet? I don't think so. I think this is easy. Energy in and out. Let's take a look through these changes on the slides. Of course, you have the fourth phase of matter, which is really cool. When you don't think about this way this phase looks, like you could picture what gases look like, sort of how they're moving and whatnot. You can picture how liquids look. You can definitely picture how solids look. Plasma, you know, like the flame of fire, the flame itself is plasma. Right? A lightning bolt is plasma. Okay? It's also called a supercritical fluid. That's a fun one. It's like a high intense pressure and high temperature. Pretty neat. Oh yeah, flame. Anyway, you saw that on the solar flare. Cool. Liquid to solid is called freezing. Wow. You know, there's a fancy term for this, and we'll learn this later in a later unit. It's called solidification. That's not so fancy, but it freezes. It gets more solid. Interesting thing about this is liquids turn to solid. Which way does energy go with respect to the substance? Out of the substance. Hold on. That means as a thing freezes, it releases heat. Isn't that wild? Like as ice forms, the heat goes out. Of course, this isn't a huge. This shouldn't be a huge shock. You have this thing in your where would you put something to freeze it? Freezer. Good. Look at you. When you put a liquid thing in the freezer, the heat, you can understand that heat leaves the substance because it goes into the walls of the freezer. It goes into the refrigerant of the freezer. Are you with me? It has this cooling agent, and the cooling is literally trying to make the outside environment colder than the substance. Hello? So it suctions the heat out of the substance, thereby freezing it. This is pretty, this is kind of revelatory. It's kind of cool. It makes sense that this has how it works. Energy decreases to do this in the substance. The exterior gains energy. This is why the freezer has to be constantly running, because it's constantly running a motor, a power, to suction out the heat. It has to exhaust the heat. That's why the exterior of refrigerators and freezers give off warm air. It has to exhaust that heat that it's absorbing.
So have you seen water in space?
I've never been to space.
No,
So
it like boils and freezes. Like I don't get that.
it's because of low pressure. There's low pressure environment. And so the difference between those things happening is fairly close in space.
It reaches the boiling point.
Right, pretty quickly. Because actually, so there's I don't have a good graph here, but when you plot a heating curve, something is frozen and then it melts, and then it gets heated up and then it boils, and then it's all the way a gas phase. Right. This is as you have time and heat. This is what happens to the temperature. Are you there? If instead you graphed, let's see, is it temperature and pressure? Yeah. If you do pressure versus temperature, it's like this. At sea level, when we're like at sea level, this is like 1 atmosphere. That's how the pressure at sea level. And anything above that, actually it's a little bit above that. Anyway, this is 1 atmosphere. At this point in time, as you are in the solid phase, then the liquid phase, and then the gas phase. And over here you've got solid, liquid, gas phase. As a substance increases its temperature, as temperature goes up, it goes from solid to liquid to gas. Are you there? This is pressures on Earth. These are all pressures that you could experience on Earth. As you go down below 1 atmosphere, up into the atmosphere of the universe, of the Earth that is, or into space, you're talking about a very low pressure. At a low pressure, it goes straight from solid to gas and reverse. Low pressure it doesn't go to the liquid directly. Are you with me? Just how water behaves. But if that doesn't make any sense, that's okay. That's not on the test. That is just bonus today. You'll see that later, though. Condensation, when gas goes to liquid, gas energy decreases. The gas loses energy, gives it off to the air, and becomes liquid. It cools down. Gas molecules cool down. Okay? Solid to liquid, as solids wiggle more and more and more, they start to flow into liquid. Energy increases in the substance. Yes? We can see this on our energy arrow. This isn't a huge shock. Boiling, liquid gains energy, becomes gas. The flowing molecules go wild afterward. Am I telling you anything that's a shock? These are all just generalized things you've been doing for a while. Evaporation can happen without much heat added. There's some minimal amount of heat added. The top water molecules can heat up just by local temperatures, and so those top molecules can go off into the gas. And vice versa, they can condense back in. This is just evaporation. Energy increases in the substance. Are you okay? Here's what I want you to do. I want you to hold your hands up like this. And I want you to imitate solid molecules, solid particles in a solid. Go. And they're pretty close together. Okay? Now, as things melt, what happens to them? They start flowing more than wiggle. Are you there? As things start to boil, they start spreading out and they fill whatever container you're in, and then condense. And then, let me get up on the screen too. And then condense. Oh, and then freeze. Are you there? What's it called when you go straight from solid to gas? Sublimation. What's it called when you go straight from gas to solid? Deposition. Hello? It deposits. Okay, cool. All right, other things, intensive versus extensive physical properties. So what we're going to do is actually practice identifying these because I feel like it's the best way to help you understand the difference between intensive and extensive. But remember, let's see if you remember. What is the difference between intensive and extensive?
Energy would go in and going out.
Okay, so that's endothermic, exothermic, but still we have a sort of a similar thread to pull at. The in and out motif. What do you think means something is intensive?
That happens inside.
It's happening inside, it's inside, it's true always. Because it's an inside quality. Are you with me? The who of who you are is always true no matter what. No matter where you go or anything else. You are who you are. Right? A lot of times, like your name for the most part. Are you there? Okay. Extensive then would be something that could change depending. I think you'll understand this here soon as you try it. I want you to look at these properties real quick and just on your paper jot down maybe next to your notes. You don't write every word. Do not write boiling point dash. Just list, just like put I or E for boiling point, and then put I or E for color, and then I or E for conductivity, I or E. I want you to try each of those. Try to answer each of those. And how many would you got? 3, 4, 8. You got 8 on the left side column and 6 on the right side column. So do 8 answers on the left side, 6 on the right side. In any space you want to. This is like jotting down just practice. I gotta check on something real quick anyway. So this is what I want you to do. I want you just to guess. I or E. You only have 2 options, like true or false. You getting it wrong will help you learn. You getting it right will affirm what you think you know. So just give it a shot. Just try I or E. Based on what you think you understand about intensive versus extensive. We're going to clarify. This isn't like a quiz. Dan, what color group are you in? Yeah. Cool, great. Okay. Here we go. Let's try some of these. Boiling point, intensive or extensive? Boiling, does it matter? It is intensive. Color. Intensive. Doesn't matter how much you have. If you have a lot or little, the color of if a substance is characterized by a color, if you have the substance, it is that color. Hello? Coal is the color dark gray to black. Are you there? If you have a lot of coal or a little bit of coal, guess what color it is? Dark gray to black. Hello? The color is what it is. Okay, conductivity. Intensive. You either, if you have it, it conducts, and it conducts, then it conducts. If you have a lot of it, it still conducts. The fact that it conducts is what conductivity is about. If it conducts better, you're talking about degree of conductivity, how well it conducts, or how effective conducting it is. Conductive, yes or no, is conductivity. Are you there? How good it does is another measure. How good might be dependent on how much it is. Are you there? You understand the difference here? All right, what about density? Intensive. It's based on its identity. Identity, intensive. Ductility, can it be made into wires? Ductility. Get this is crazy. What do you call the things that carry air to the vents in the walls? Ducts. Air ducts, right? Okay. What if those ducts were microscopic and could fit between your fingertips, and instead of transferring air molecules, it transfers electrons? You'd call those wires, right? Wires are like microscopic ducts, electron ducts instead of air ducts. Are you there? So ductility, that's why it makes sense. It's called. Okay. Why don't they call it wireility? I don't know. That's a weird word too. So go figure. I like ductility better. Plus quack. You know what I mean? Anyway, hardness, intensive. Doesn't matter how much you have. The substance has a hardness value, part of its identity. Length. Hey, if you have more, then you can have more. Hold on. This is the phrase you want to use. If you can have more, you can have more. Hey. Oh, how are you? Good to see you. Okay. Are we all right with this? Is this? It's all good? Okay. Great. Good to see you. She was the first period in the spring semester last year. That's for you. Hey, look. If you say, if you have more, then you have more. So everyone say, if you have more, then you have more.
If you have more, you have more.
So if you can say it about a characteristic, then that's extensive. So if you have more, then you'll have more length. Hello? All right. Magnetization. Intensive. Let's skip to the punchline here. Magnetization intensive, malleability intensive, mass extensive. Because if you have more mass. If there's more, then you'll have more mass. Cool. Get this. If you try to say that about malleability, if you have more, then you'll have more ability to make into sheets. No. It either can be made into sheets or it cannot. So, if you have more, then its boiling point will be more. No. Boiling point is based on its identity. If you have it, that's its boiling point. Hello? If that sentence is false, then it is intensive. If it's true, then it's extensive. Do you understand the device here we're learning? Okay, good. Melting point I, odor is I, because what is the odor? How do you qualify the odor? Okay, it kind of smells like lavender. Okay? Like lavender is the quality. Now look, the intensity of the odor, how deeply, how strong is that smell? Okay, the fact that it has a smell is odor. The intensity of the odor could be extensive. Are you there? Degrees of amount is for extensive. Intensive is just present. The temperature. Having something can register a temperature. Having more, like what temperature it is right then and there, is just, is it present or not? Okay? Volume is extensive. If you have more, then you have more. Now hold on. For some reason I thought I just read. Yeah, good. I thought for some reason I just read a source that tried to say temperature was extensive. It is not extensive anywhere. All right, how about this? Identifying among the four classifications. Of course, you had your worksheet to work on, which we'll go over in greater detail later. But right now, let's do some practice up here. You have 10 examples again. Try these. Take about let's say 48 seconds. Okay, 49. Fine. You bit my arm back. Need about 10 more seconds. Evan, you got these? Okay, good. Need more? Who needs 10 more seconds? Okay. All right. How about these? Check yourself. Oh, I don't know why I should have done HM. I don't like putting, just don't like the word hoe putting up on a piece of paper. You know? I don't have to. Yeah, are you okay? I was practicing some information over here. All right. Any questions? Which one of those were troublesome? Which one?
But I guess you could shine like through it.
So yeah, so blood is a colloid. Blood you cannot shine light through. It actually has elements that will settle out over time, but for the most part they stay somewhat dissolved. They will settle out sort of like milk. Like milk doesn't really settle out. It just undergoes some extra reactions and then some stuff curdles, right? Your blood can sort of do that. For its first draw though, blood stays suspended, so it's a colloid. You cannot see through blood. In fact, if you can see through blood, you probably are on some sort of medication. Chrome is a blend. Let's see, I have it on this other page what chrome is made of. I think I have it on this other page. Chrome is a blend of metals, and metals don't chemically combine. Okay, it's chromium with other. It's chromium, a type of element, but it's plated with other metals in it. Okay, so chrome is a blend of metals, but metals do not chemically combine. They just mix. They mix so well you can't tell one particle from another. Are you there? Bronze, you can actually tell one particle from another. Brass, you cannot. Brass, chrome, silver cavity fillings, not silver, silver is the element. Silver cavity fillings, brass, chrome, steel, silver cavity fillings. Those are all alloys that are homogeneous. Are you there? Okay, those are homogeneous mixtures, obviously, of solid that you cannot see through. Done. Anything else? Cool. All right, what about another practice? What about difference between homogeneous, heterogeneous in greater detail? another 55 seconds. Never seen that before. All right, so here's what we got. Bronze is our heterogeneous example of a metal alloy, although for the first time I just found an example. Bronze includes many metals in it, but I just found one example of a source that tries to say that it's homogeneous. But it is just not homogeneous. It is heterogeneous. You can actually tell the particles. You can see little specks. If you look close enough, it looks like little tiny specks. Make sure there's no other issues on this page. Good. All right, what questions do you have on that one? Salt water. Okay, you dissolve salt in water. If you put salt in water and you stir it up, or don't even have to stir it, it eventually will dissolve all the way, and you won't see the salt anymore. You can see through it, and they mix together. And it doesn't ever settle out. It's a solution. Ocean water is not just doesn't just have salt in it. It has like algae and dust and dirt and sand and other things that if you put in a glass, they'll settle out. If you don't disturb it, it'll settle down. Are you there? The fact that it can settle means it's a suspension, which means it's heterogeneous. Are you there? Will not settle, solution, therefore homogeneous. Are you following the logic here? Yes. Okay, so coffee just grounds with plus water. The coffee stays dissolved and you can see through it. If you have a solute or if you have a liquid mixture and it doesn't settle, so not a suspension, and you can see through it, it is most definitely homogeneous or a solution. Are you there? When you put cream in it though, cream disallows you from seeing through it, it will not settle, okay? But since you cannot see through it, it's not a solution. It's probably, being liquids, a colloid. And it turns out it is. That's just what it is, a colloid. But thinking logically through it, can't see through it. When you coffee you can, when you put cream you cannot anymore. So coffee with cream makes it not. Water with food coloring, the water just turns the color, but you can definitely see through it. Some of these you have to have had experience, like you have to actually try out water plus food coloring. Have you ever seen this occur? Let me see, is there anyone, you see a water bottle around you that's not yours? You've got food coloring in this.
But I am just like throwing them bad girls on the paper.
What do you do?
Yes. Yes. Yeah. What kind of person? You don't try to trust me. That make you. That'll make you way over there. I want to accept it.
Okay, well, here we go, watch this. Water and food coloring eventually mixes here.
And it's going to settle.
It's not going to settle. It's hydrophilic, so it's going to spread out. I'm just speeding up the dissolving. You can see through it.
That is
Translucent is still seeing through. Okay. All right, here we go. So what I need you to do is, on a half sheet of paper, you can share, take a piece of paper, share it in half, give one half to you, and you can take the other one, or just fold it in half. I don't care, but make it a half sheet of paper, please. Number 1 to 5. I want you to try it, too. You're going to turn it in, but you can still... Oh, yeah. You're gonna turn it in. If you have liquid mixture see-through, does it settle?
This is over the freaking deep crap.
So that's all.
I don't know. I didn't know.
Like that fast? I drink it.
Maybe not that bad. Really big too.
6 seconds. It's still a rough one.
You need to be there. Can you be in the rain Saturday?
But y'all, it's live streaming.
It was so shaky.
I say might because I don't want to.
Rossi wants to.
I want to. I mean, I have to remember also. That's part of it.
Rossi wants to see your face when you stay.
Well, unfortunately, I can't get away. Can't get away from here to get to Lagrange. I will be cheering you on though. Rooting for y'all to come up on unexpectedly on that old Jeffersonian folks. All right. First question on your page here, number 1. So no notes out or no notes available to look at. Just close, put away is the best way to do it. Number 1. Give it a shot. You ready? Now, hey, don't shout. Just write down. Right. So on your paper with pen and paper, write it down. Name this piece of lab equipment on your paper. Don't say it. Just write it. Will you close your computer, Evan?
A little bit.
Thanks. trying to name this piece of lab equipment. Spelling, yes, this is for a grade. Spelling is, I'm the loosest today on spelling, but it needs to sound close enough. When I read it, it needs to sound close enough to the real thing. Not like the thing that they're pouring, like holding that piece of glassware, not the person's hand. That's not allowed. Okay, number 2. What should you do if you break a piece of glassware? Don't say it, write it. Accidentally break a piece of glassware. Or on purpose, I guess, but hopefully accident. Piece of glassware breaks under your watch. Write down your answer, don't say it. Number 3, let's convert this measurement on your page. Show one step of work at least. It can be very minimal looking. You might not even think it counts as a step, but it probably still does. One step of work. One step of work. Okay. Number 4, write your answers, of course. An unknown P has a density of 1.76 grams per milliliter. That's its density. Will it sink or float in water? Will it sink or float in water? This is a sink or float answer, one of those two. Write it for A, and then B, answer Y. It can be very brief. All right, and then number 5. A rock with volume of 500 milliliters has a mass of 250 grams. What is the rock's density? Show at least one step of work, and of course your answer. Oh, just go no, we'll grab the picture. You should grab your calculator on the way in too. All right, if you're at home doing this, you can do this on a sheet of paper. Just take a picture of your answers and send them to me. I'm going to go over them right now, so I'm turning off the microphone. Anyway, send me a picture. I need the timestamp to be, well, around whenever you're watching it, but ideally it's about right now, 9:15. So, go dogs. All right, we're back at home, viewers. Okay, so we put the periodic table all the way together. This is how it looks. I want you to notice some things, though. The way this works here, it actually shows it right here where it fits in. You see it? Okay, so that actually these squares, which would be like scandium, yttrium, what are the next two squares underneath? What goes under scandium, yttrium? What the next two under here? The next two under here are these, this 5D and 6D. Oh, don't look at my booty. 5D and 6D. 5D and 6D electrons, the ones that are labeled 5D, 6D right there, are called lutetium and lawrencium. Are you there? Does that make sense? Lawrencium, lutetium, lawrencium. So that underneath here goes scandium, yttrium, lutetium, lawrencium. Are you there?
Yes.
And then the first one of these whole rows here is lanthanum and actinium. That's what this series is called, lanthanide series and actinide series. So you better act to right. Actinide. Are you there? Does this make sense on the periodic table? Whoa.
Yeah.
I almost lost it. Do I want to say anything else? Yes, I do. So periodic table is a great tool. We mentioned this before already. That the rows or periods tell you what?
Electron shells are
Number of energy levels are used. Electron shells are used. What does it tell you again? Number of electron shells used. Yes? So let's put that into action. Cobalt. How many electron shells can its electrons use? What period is cobalt on? It's on 4. So it has electrons occupying the 4th energy level. Are you there? Okay. Let's say, okay, barium. What electrons or what energy level does it have electrons occupying? 6. And get this, it has electrons that occupy the 6th energy level and every energy level underneath it. So whatever they have as their outer, every electron underneath it is also in there. Hello? So let me paint it this way. Cobalt has every electron that iron has plus one more. Are you there? Barium has every electron that cesium has plus one more. Are you there? You see how this works? Cesium has every electron that what? Xenon. Xenon. Cesium has every electron that xenon has except what? One more. Are you there? Now, later on, we're going to actually represent this in an image, in an illustration, a specific kind of scientific one. But I just want to point out some of these precursory things. Are you there? Okay. What does group number tell you? The number of outermost or valence electrons. Now notice, we only care about labeling these groups. 1 and 2, A, 13, 14, 15, 16, 17, 18, aka 3A, 4A, 5A, 6A, 7A, 8A. We care about labeling just those groups. We don't label these groups because these groups have unpredictable outer electrons. They're not totally unpredictable. They're just statistically predictable, which means they're not consistent. Hello? Depends on the day, the time, the circumstances. We'll get into those later, but that's why we don't label those group numbers. Also, you can see how wonky this is. Look at the way they're labeled on here. 3B, 4B, 5B, 6B, 7B, 8B, 8B, 8B? 1B, 2B? Huh? Are you with me right now? The B group labels get real wonky. That's another reason why we don't do what we do with the other groups. Hello? So, here's the question, putting legs onto this. Brian, you can help me with this one. Beryllium. How many valence electrons does it have? 1. No. 2, because why? It's on group 2. Brian, magnesium. How many valence electrons does it have? Because why? Group 2. See, Emily. Oh, perfect. Gallium. How many valence electrons does it have?
3.
Because why?
Group 3.
Group 3A. Yep, group 3 or 3A. You can just say group 3 like you did. That's good. All right, Cam. Selenium. How many valence electrons does it have? Because why? Because why? It's in group 6. Say it's in group 6. There you go. There you go. All right, Ian. Silicon. How many valence electrons does it have?
4.
Because why?
It's in group 4.
Hello? How about one more? Evan. If you're not here, you... Argon. How many valence electrons does argon have?
8.
Because why?
It's in group 8.
Yep. What about radon?
8.
Because why? Doesn't matter what row it's on. It's talking about what outermost or valence electrons. Are you there? All right, and then we do our count our loss or gain of electrons. Right, our charges, or what we used to call charges, you now call oxidation number. Everyone say oxidation number. Everyone say 1 plus.
1 plus.
2 plus.
2 plus.
3 plus. Na. Everyone say Na.
Na.
3 minus. 3 minus. 2 minus. 1 minus. 0. Those are the charges or oxidation numbers those elements will form. Hello? Do you follow what I'm saying right now? All right. Copper. What is, you can look at your reference page, you're a Rainbow Pack as well. What is its atomic number? 29. What is its atomic mass? 63.5 is what yours says? Right? What is its symbol? I see you too.
Nah.
And its name is copper. Do you understand how to use the periodic table? That's the basic extent of it. Okay, but the periodic table tells us a whole lot of other things. Clearly, you can tell what row something's on. But wait, the row also tells you electrons or energy levels the electron uses. Hello? You can tell, oh, it's in the group number 7. Yes, and you can tell something else because of that group 7. 7 valence electrons. Are you there? There are layers to this information. And this is where we come across what's called the periodic trends. And I know you're graphing it a little bit, and I wasted too much time today. Yeah, I freely admit it. It was me. I did it. Oh, where's these slides? Okay. Let me get to them real quick. Sorry.
When's our that graphing project thing?
The graphing project is due tomorrow. I'm sorry. No. It's not due tomorrow. That's what I meant to say. It's not due tomorrow. It's due Tuesday. I re-change that up. You gotta do the questions that go with it. But first, I want to get down. This is what I want to make sure you have in your notes today. This image demonstrates the trends and how they go across the periodic table. The periodic table demonstrates electronegativity and ionization energy and atomic radius along it. Meaning this. Electronegativity increases up and to the right. Ionization energy increases up and to the right. Atomic radius increases down and to the left. Here's what you have to be able to do with these understandings. You need to be able to know the definitions of the 4 of them. The slides prior, and on Monday and Tuesday you should have copied these down. Atomic radius, ionic radius, ionization energy, electronegativity. We'll have to talk more about them tomorrow, apparently. But those 4 you should have already written the definitions for. Did you do that? Okay, you need to have done it. You need to do it if you haven't already. They're on the slides. Copy a little diagram of the shape of the periodic table, and then write these arrows on there just so you can demonstrate this into your notes. You can study it this way. But here's how this works. This is all you have to be able to do. Know the definitions by studying what you write down. Okay? Apply that to a little bit extent using your graph data. Your graphs help you answer the questions. Again, I'm going to walk you through that some more tomorrow, so don't freak out. We still have tomorrow to walk through a little bit and begin reviewing. Monday to review, Tuesday to test. We're doing great. I've been taking it slower on things that I feel like you needed more time on, and we're going to be fine. But here's the skill. Check this out. Here's the skill. We're going to go over why these highest and lowest are what they are in a minute, but here's the skill. As you go this way, electronegativity increases. So you can tell me this. Elena, cobalt or iron? Which one has a higher electronegativity? Cobalt, because it's further to the right, and electronegativity increases to the right. Are you with me? I'm going to be asking about next door or very close to neighbors. All right, cadmium and palladium. Macy, cadmium and palladium. Which one has a higher electronegativity? Cadmium, because it's further to the right, and electronegativity increases to the right. Are you there? All right. Christian, aluminum or indium? Which one has a higher ionization energy? Because why? Further up, and ionization energy increases up and to the right. Hello? Okay. Elena, I know I just called you, but I just got a random one now. Magnesium and strontium, which one is higher ionization energy? Magnesium, because why? Further up, and ionization energy increases up. Hold on. AJ, real quick. Atomic radius. Here we go, look here. Barium or scandium? Which one is larger in size? Because why? Further down and further to the left, atomic radius increases to the left and down. Does this make sense? I'll give you an example about how this is going to look on the test tomorrow, but do you think that skill of doing what we just practiced is difficult? Are you going to be okay?
Yes, sir.
I think so too. Okay, so you can pack it up. I said that for posterity. I already knew most of you packed up. Go dogs. See you tomorrow.
Don't you go down.
Thanks for watching. Tune in next time for another edition of Night Chemistry.